Hi everyone, my name is Lydia, and this is what I wish they had taught me about econometrics and introduction. So far, we have seen the OLS as a projection, the fitted line that is the closest possible to the line, to the data cloud, and the residuals stand at the right angle. And we've also had a bit of an introduction to the OLS matrix notation. So now it's time to make the full circle and make the connection of why the OLS matrix notation is so important to actually understand and make better sense of the concept of the OLS as a projection. If you remember, in the previous videos, we had this graph where we showed the subspace of x1 and x2, and we also had y. Keep in mind the y is shown here to kind of go over the subspace to give you an idea that it's not part of that subspace. So when we want to project a vector y into the subspace that it's defined by x1 and x2, the projection, which again we called the fitted y hat, is the point in the subspace closest to y. Okay? And the only way that we can do that, so dropping a vector into a plane, the closest point is always found by a perpendicular drop. And that's why we drew this last time by imagining that we have like the perpendicular drop, and this was our projection. Okay? So again, keep in mind the projection. This is the closest point to y in the subspace. And the other thing that you need to remember is that the vector of your residual, epsilon, or as we noted in the previous video, simply by the Latin letter E. So this is just the difference between your true and fitted value, is the shortest possible difference. Okay, and by geometry, as we can see, this shortest difference occurs only if this residual is perpendicular to the subspace, because keep in mind, if this is the distance, this is exactly the residual. Okay, so a projection into a subspace produces a residual orthogonal to the subspace. Equivalently, projection, perpendicular residual, normal equation, uncorrelated residual, or minimized squared error, perpendicular residual. Now that we have made this point even more clear, let's see well, how does it exactly move into our OLS matrix form? So if you remember, in matrix form, we're going to write our model as y equals to x, which was, remember, the matrix where all of our x variables were stacked up, times the beta vector plus the error term in here. Now, we haven't seen the proof of it so far, so for now, let's just take for granted that we know the beta hat solution is simply x prime x minus 1 x prime y. Okay? Now, if we plug this solution that we know on the beta into the actual solution in here so that we can get the estimated model like we always do, that means that our y hat is simply going to be x times our beta hat. Remember, in the estimated model, the error term has no space, being equal to x times x prime x minus 1 x prime y. This entire block of information that you see right here, well, that is what we call the projection matrix. So the result of all of this is the projection matrix. Okay, most of the time in most of the books, you'll see it noted as like P. Now, what is this projection matrix? The projection matrix is basically taking over any vector, and in our case, it's the y, and projects it into the subspace spanned by the columns of x. Basically, the same process that we just did by drawing this graph right here. So you can think of it in other ways like this. If you imagine a light that is shining straight down onto a line or a plane, the shadow that you will get is just the projection. Okay, that shadow, it's literally your fitted value of the y hat. And it lives exactly in the subspace that these two x's in here, x1 and x2, have created. Okay, now let's go back to the error, to the residual. That we defined as the difference of your y with the projection. Normally, if we use the OLS formulas, the normal equation, or the orthogonality condition, as we've been calling it, is just going to say that they are orthogonal, right? We can just rewrite it as saying, well, what is orthogonal? Well, it's the subspace, right? Times the residual, okay? We have to make a little bit of an adjustment in here. We will see in another video what the prime and the -1 really mean in terms of matrix notation. But this this prime in here has been introduced because we need to make sure that the dimensions of this x vector and the column vector of the residual match, so that we can multiply basically in the matrix dimension and get then a result that it's just a scalar 0. In geometry language, again, it just means the residual is perpendicular to every column of the x, and therefore perpendicular to the entire subspace that it's being generated by x. So that's why the OLS residual arrows all meet like the fitted line at 90 degrees when we did the projection. As in, why is this important? So again, my matrix notation reveals the dip structure behind OLS. In here, we have shown that the fitted values are a projection. Fitted values are a projection, which we can also write as y being p, the projection, times the y. The projection is orthogonal, which we just saw in here. Keep in mind, these in most books can also be written simply as x prime e, because we've said that the e sometimes refers to the residual when it's not in Greek letter. Okay. And at the same time, what we're saying is that the regression line is the closest point to y in the space spanned by x. We saw that with the summation notation. Now it makes more sense with the matrix notation and why we had to do the graph with the perpendiculars. I hope this was helpful, and I'll see you in the next video.